week's presentation, Local Government's Efforts to Protect and Sustain Lake Chapala, presented by Kara Pratt. Have you ever wondered what local Mexican government entities are doing to protect our natural environment in the Lake Chapala region? In this talk, we will learn about aquatic weed management, environmental education, efforts to combat and adapt to climate change, and the creation of natural protected areas surrounding Lake Chapala. Kara Pratt grew up in Wisconsin. After graduating with degrees in environmental policy and international relations from Drake University, she joined the United States Peace Corps in rural Paraguay, working in a grassroots environmental conservation. Now she joins us as a United States Peace Corps response volunteer, working in natural resources management with the APROMEDIS, which is the International Municipal Association for the Environmental Protection and Sustainable Development of Lake Chapala. So she's going to join us and talk to us about what she knows. So that should be fabulous. Today's meditation is led by Carl Holman.
I want to read to you a poem which I hope will put you in touch with your truest inner self. So get comfortable in the best way you know how. Silence your random thoughts if you can. And turn the words you will hear into images of your imagination. Get in touch with your deepest consciousness, the still points. I'll read you a poem of a man who's a native of a Caribbean island called St. Lucia, who died last March. I had the fortune of meeting him in 1992 when he came back with the Nobel Prize of Literature. Love after love, Derek Walcott. The time will come when with elation you will greet yourself arriving at your own door, in your own mirror, and each will smile at the other's welcome and say, sit here and eat. You will love again the stranger who was yourself. Give wine, give bread, give back your heart to itself, to the stranger who has loved you all your life and whom you ignored for another, who knows you by heart. Take down the love letters from the bookshelf, the photographs, the desperate notes, and peel your own image from the mirror. Sit and feast on your life.
This week's presentation, Reality Check, Quantum Implications for a New Era, presented by Pam Wolski. Physicists, philosophers, and poets have been fascinated by quantum physics for nearly 100 years. What actually is quantum theory? Why has it intrigued such a broad spectrum of society, as evidenced by book titles ranging from quantum reality, quantum enigma, and quantum healing to quantum poetry, quantum forgiveness, and quantum spirituality? Pam will explore with us these questions from a broad perspective, ranging from science and medicine to philosophy and spirituality. She will consider the question, what does quantum physics tell us about the nature of reality? Pam was a book editor and a teacher of writing and math near Chicago, Illinois, before moving to Mexico with her husband Tom in 2013. Quantum physics has fascinated her for 10 years, and she enjoys learning how it has been applied, actually and metaphorically, to so many areas of life. Please welcome Pam. 1, 2, 3. Can you hear me?
No.
No? Yeah, we got a little bit, maybe.
Okay, well, thank you very much, Kat, for your introduction. And thank you to all of you for coming out on a Sunday morning to hear about quantum physics. So before we start, I'd just like to have a little familiarity with who you are. Can we have, by a show of hands, how many people have some familiarity with quantum physics? Maybe through a book? Wow! Now I know why you came out this morning. Okay, that's great. That helps me to know you a little bit better. I want to mention, as you know, if you know anything about quantum physics, it's a very complicated, in-depth subject, and it'd be hard to cover in 35 minutes. So I've created a Facebook page called Quantum Reality Check. It's at the top of your handout, the words, and I'm going to be posting my talk on that Facebook page, and as well as many links and other sources of information that you could look further into this topic, if you'd like. Okay, before I get into the subject of quantum physics per se, I just want to say that I'm not an expert in quantum physics, but as Kat said, I have had a fascination with it. And I'd say maybe how it started was when I was about 10 years old. My Uncle Charles, who was a high school physics teacher, he showed me the wonders of a Mobius strip. Maybe you're familiar with it. It's a surface that has one side and one edge only. Well, I was just fascinated with this, and I thought physics must be really cool. So when I got to high school, I took physics and math courses, and it didn't hurt that since there were only 4 girls in my all-girl high school who wanted to take physics, we got to go to the boys' school, which was close by. So that made it fun too and interesting. I really enjoyed the puzzles that math and physics present, and it really comforted me that if I didn't know the answer, somebody did. My teacher, my father, another student. It was very comforting. When I went to college, I continued with my math and physics in my first year of college, but as you know, in college there's many other things that I could become fascinated by, and that's exactly what happened. I got involved in English, literature, philosophy, psychology, spirituality, and so math and physics kind of went in the background. I thought, I can go back to it. So actually spirituality really fascinated me, and I got involved with, since I was coming from a Catholic background, I thought, well, I'll try other religions. So I explored Eastern religion and got involved with yoga, meditation, and several Hindu gurus. You may wonder, what does this have to do with quantum physics? Well, you may be familiar, there was a book published in 1975 called The Tao of Physics. This is my senior year, and this fascinated me because I was already into Eastern religions, and this was talking about the parallels between modern physics and Eastern mysticism. So that just kind of reinforced my interest. Now, since my talk is about quantum physics and not spirituality, I won't go into detail on this, but I just want to say for the record that 10 years later, after in 1984, I had moved away from Eastern religions and was into non-denominational Christianity. So I just wanted to clarify that. So we fast forward to 2008, and I began noticing that many people were talking, in fact saying amazing things about quantum physics. For instance, Rhonda Byrne, in her book called The Secret, she says, quantum physics tells us that the entire universe emerged from thought. You create your life through your thoughts and the law of attraction. Shirley MacLaine, Dancing in the Light, quantum physics was saying that what we perceive to be physical reality was actually our cognitive construction of it. Hence, reality was only what each of us decided it was. Another writer, Willis Harman, in a book called Global Mind, said, Bell's theorem, which is part of quantum physics, demonstrated that everything in the universe is connected. So I thought, well, these are quite amazing claims. I don't remember this from my physics classes, so I'm going to explore this. And so since that time, I began a more serious study of the subject of quantum physics. Did it really say the things that I was hearing it was claimed to be saying? And actually, the more I looked into it, the more intriguing it became, and I realized this is the greatest puzzle of all time. People of the mental, intellectual caliber, such as Einstein and many others, had been trying to figure the puzzle out. They still are today. Brian Greene is one of the main proponents of quantum physics study, and he says the jury is still out. So that is really was interesting because what I liked about physics and math when I was in high school and college was there was always an answer. And now I found out there maybe not be an answer. Well, this really intrigued me even more. I thought, maybe I can figure it out. So I armed myself with books and many articles over the years and trying to figure it out. And, you know, I'll just mention there's a parallel. There's a dog in my area who chases birds, and I just get such a kick out of him. I think, does he really think he's going to catch those birds? But he had such fun trying, and I feel that's kind of like me with quantum physics. Well, I keep trying to understand it. I'll keep trying, and I'm having a lot of fun doing it. So, as I found out later, I'm not the only one who has a hard time understanding quantum physics. Richard Feynman, theoretical physicist, winner of Nobel Prize in Physics, 1965, he said, I think I can safely say that nobody understands quantum physics. Now, if you appreciate this and you don't take the lecture too seriously, just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does act like this, you will find her a delightful, entrancing thing. So that's the way to look at this lecture. Don't try to understand. So this is how he brilliant theoretical physicist, introduced his lectures. So Niels Bohr, another pioneer theoretical physics, said, anyone who is not shocked by quantum theory has not understood it. So if you do understand it, you'll be shocked. So now the question is, what is quantum physics? Well, physics is a study of science of physics is the science of matter and energy and the interaction between the two. Quantum physics is the branch of physics that deals with the very small, subatomic, atomic particles. The word quanta is from the Latin word meaning how much, and they had found out that atomic and subatomic matter absorbs heat and light energy and emits light energy in bursts, little packets of energy. They call them quanta. That's where the name comes from. This is in contrast to Newtonian classical physics, which is a study of the large planets, the everyday world that we're so familiar with, and where determinism applies. We'll find out quantum physics, it does not apply. Quantum physics is the basis of much of our current technology. Almost any device, transistors in personal computers, cell phones, lasers, CD, DVDs, flash drives are all based, they have quantum physics as part of their makeup. MRIs, nuclear power, electron microscope as well. Future prospects for quantum physics are quantum computers, which are to run exponentially faster than the current, quantum cryptography, which promises guaranteed secure transmission of information, and even quantum teleportation, where a particle could be teleported instantaneously somewhere else, and they're doing that with subatomic particles at this point. Brian Greene is in one of his videos talks about the possibility of teleporting a person, such as in Beam Me Up, Scotty, as we all remember. So, by the way, I want to draw attention to the handout that has all kinds of wonderful videos, books. Some of them are available here in the LCS library, others online, Kindle form, etc. That the highest recommendation I have is for Brian Greene's book. It's just excellent and really makes it accessible to the general public. He has an excellent Nova documentary, that's the first one on the list here, called The Fabric of the Cosmos, Quantum Leap, and several World Science Festival videos, which I would highly recommend. Okay, the double slit experiment. Maybe if you're familiar at all with quantum physics, you know that term. Richard Feynman said that the double slit experiment contains all the mystery of quantum mechanics, the peculiarities, mysteries, paradoxes, bearing nature in her most elegant and difficult form. So what is the double slit experiment? On your handout you'll see two diagrams. One of them shows a water wave going through two slits. This is one. And as you can see, when a water wave goes through two slits, it splits up into two concentric waves which interfere constructively and destructively. So when the two crests come together, you get a more intensity. When two troughs go together, you get an intensity. When a trough and a crest come together, you get a cancellation, which is why you get the familiar interference, light, dark, light, dark, light, dark. That's waves. Now, with an electron, they were always thought of as particles, but they found that when they shoot electrons through a double slit, they actually get an interference pattern, which is really astounding if you're thinking in terms of particles. How can particles form something that only waves were thought of to, they thought only waves could form an interference pattern. So they thought, okay, we're going to slow down this electron gun and shoot them one at a time. We're going to find out which one of these they go through, which slit. And they found that when they turned it down to one electron at a time even, it still formed an interference pattern. Totally astounding. Wait a minute. One particle going through at a time, how can that act like a wave? They thought, aha, we're going to catch it in action. We're going to put detectors by these slits. When they did that, amazingly, the interference pattern disappeared. It's like the electron knew that it was being watched and decided to act like a particle. Well, you can imagine that just shook up everybody. Nobody anticipated that. It was contrary to intuition and really contrary to the current science. What it said really was that particles can act like particles, and electrons, and really any subatomic particle, protons, neutrons, all of them, they've tested them. They can act like particles and they can act like waves. So it's like a wave-particle duality. Niels Bohr called it complementarity. And actually, they've also discovered that waves can also have particle-like qualities. They call them photons. This was discovered by Max Planck and Albert Einstein. Okay, other features of quantum physics, as if that wasn't enough. Schrodinger's equation, Born's rule, superposition, collapse of the wave function, measurement problem. A lot to cover. So, like I said, for more information, you can pursue this later. But I will try to summarize. The scientists wondered if a single electron, while in motion, might spread out into a wave. So Aaron Schrodinger came up with a wave equation that seemed to describe this. They argued, the scientists argued about what this represented. Finally, Max Born came up with he devised a thing they eventually called the Born's rule, which is a way to interpret this equation, this wave equation, in the sense of the electron being a probability wave. The wave is not smeared out, but instead it's a probability wave with the size of the wave in any one location predicting the likelihood or probability that the electron would be randomly found there. So, and they have found that this Schrodinger equation is phenomenally accurate. When in experiments it does predict the probability of an electron ending up in a certain location. However, they never know where a particular electron is going to end up. That's always random. But the overall, over time, and run, is that the probability wave describes the probabilities of where the likelihood of the electrons will end up. So at the time, Albert Einstein did not like this idea at all. In fact, he continued to not like it till he died. He said, God does not play dice. This is too random. And Niels Bohr replied, Einstein, don't tell God what to do. So, okay. Another feature of this is the word, concept of superposition. Actually, what they think is this electron doesn't just have one or two or three locations. No, it's got every possible location. It's impose all these different possibilities, and then they add those up in order to get the probability wave function. But at the time of measurement, it collapses the wave function, and the electron always appears in only one location. So there's its particle quality. So the quantum measurement puzzle, quantum measurement problem, is how does an experiment making a measurement cause a wave function to collapse? They don't know. They've been trying to figure out. And why is there a difference in how quantum mechanics treats atomic particles, subatomic particles, and how it treats the measuring device? The measuring device is made of subatomic particles. Somehow, though, this measuring device has an effect on it in a wave. And where's the border between the subatomic world and the bigger world? And how do the two sets of rules interface? When you've got the small world with its quantum laws, and you've got the big world with its more classical laws. How do these interface? Because in our real world, of course, we don't see things in many places. We see them in one location, like a particle. Okay, other key features of quantum mechanics are, some people say this is the key, is the uncertainty principle. Werner Heisenberg formulated and discovered this in 1927. And it says that there are certain properties of particles that cannot be measured at the same time. For instance, position and momentum. Momentum is mass times velocity. So if you measure one to any kind of precision, the other is totally not precise. If you measure the other to any precision, the first is totally imprecise. At first they thought this is because the measurement device affects the thing that you're measuring, and it disturbs it. But they have found out since that that's not true. The reason the uncertainty principle holds true is because of the wave nature of particles. Einstein, when he heard about this, he said, I don't like this. I like to think the moon is there even when I'm not looking at it. You know, it should have a position even though it's not being observed. Another key feature of quantum mechanics, by the way, quantum mechanics is the same thing as quantum physics, is the same thing as quantum theory. It's quantum entanglement. The math of quantum mechanics predicts that particles can become entangled, where one part will be one in the lab, the other part could be on the moon, and somehow something that happens over here will affect the one up there. Like, no way. You know, Einstein said, there can't be. He called that spooky action at a distance. So, phenomenally, in 1964, a brilliant Irish physicist, John Bell, devised a way to test this, called Bell's theorem, yielding Bell's inequality, and there was a way to test whether or not this particle here could affect that particle there. It's the idea of local realism. The thing that Einstein had presented was called the EPR paradox. Again, you can look that up. And that is based on local realism. Locality means I can only affect what's right in front of me. I can't affect something over there faster than the speed of light. Realism means things can actually have their properties before they're measured. They don't get their properties when I'm measuring them. They had it all along. So based on these two assumptions, John Bell realized that certain mathematical things should happen. It's quite complicated. Brian Greene does a really great job of trying to explain it. And at any rate, at the time that this was discovered in 1964, they didn't have any way to actually do the experiment. It was just more of a mathematical thought experiment. Again, amazingly, in 1982, experiments were able to be done. And John Clauser was the first one. Elaine Speck, I probably maybe not be saying that right, French physicist, have been able to do the actual experiments. And amazingly, they confirmed quantum mechanics, that something over here could have some correlation with something way out there. The thing here would be in a superposition state where it would have the possibility of going up, down, up, down, up, down. But when it's measured, it snaps into position. That snapping into position makes that one snap into position, they found out. Totally mind-blowing, mind-boggling. However, they want to point out that these are correlations, not connections in the sense of communication faster than the speed of light, which is precluded by the theory of relativity. Okay, this leads some people to imply. We talk about implications. What are the implications of quantum physics? Some people will take this to imply everything's connected and everything is one. So we're going to talk about that in a minute. There are many varied interpretations and implications of quantum physics. It is the most successful theory physicists have ever discovered, but they are still arguing about what it means. It works, but they don't know why. Referring to a particle's probability wave, questions can be asked, some people say it is the particle. Some people go, no, it's just associated with the particle. Others say it's just a math device for describing the particle. Others say it's the embodiment of all we can know about the particle. Still being debated which of these is true, and as Brian Greene says, the jury is still out. Various interpretations, there's like 15 at least, that are listed in Wikipedia, for instance. But the top ones are, I'll talk about three of them very briefly. You can look into them more if you desire. Copenhagen determination. This was formulated by Niels Bohr, Werner Heisenberg. It says that until one measures a particle's position, there's no sense in even asking where it is because it does not have a definite position. Says when we measure the electron's position, we're not measuring an objective pre-existing feature of reality. Rather, the act of measurement is creating the reality that is being measured. It forces the particle to relinquish all of its possible places it could have been and to select one definite location. Well, this is a mind-blowing concept to people. Einstein did not like this. Schrodinger did not like this. Schrodinger devised a thought experiment called Schrodinger's cat, which is very interesting. He says if you have a cat in a box and you put some kind of a poison in there that is in a superposition, maybe it's going to kill it, maybe it isn't. And what state is the cat in? Is the cat half dead and half alive? Well, of course not. So, however, according to the math of quantum mechanics, that's what happens. Things are in this superposition state. Okay, another interpretation is the many worlds interpretation. Maybe you've heard of parallel universes. That's where this idea comes from. This interpretation says reality consists of steadily increasing number of parallel universes. So all possible outcomes occur. There's no collapse of the wave function. All the possibilities really happen. It's just the universe splits off and every one of them is going on in a different place. It's like, whoa, that blew everybody's mind. So in that locality is not applicable there, and the superposition states are taken literally. Okay, let's talk about two questions arising from considering the implications and interpretations. Do we create our own reality? And if so, in what ways? Does consciousness cause reality? Some people say it does that are interpreting quantum physics. However, it's important to point out that the experimenter can affect the outcome of an experiment, revealing whether an electron is a particle or a wave, depending on which measuring device they use. But that's a whole other thing than to say that you can create your car or create your soulmate, or some people take this to a more of a spiritual, personal level. That's a whole other thing. I mean, maybe that is true. I mean, you can create in some sense, but that's not what quantum physics says. Quantum physics is saying you're going to create the property of an existing object. It's different. Okay, of course, our attitudes and thoughts can affect our reality. We know that, but it's quite a leap, quantum leap, to say that you can create physical objects through thinking. Also, physicists have determined that the role of consciousness in the measurement process is not really significant because the measurement can be done by a non-human device. So, the next one to consider is everything connected? Is everything one? Okay. In my reading, the term non-locality was used in various ways. Sometimes it refers specifically to entangled particles. This particle can affect that one over there instantaneously. Other times it's applied to when the wave function collapses, which is a different application of the word. And sometimes it's applied to the whole universe, because some people say the universe is, since it's composed of quantum particles, everything must be entangled. Well, Brian Greene addresses this, and he says that, I'll just read this, I'm not going to read the whole thing, but I'll just say that he says two things can be separated by an enormous amount of space and yet not have a fully independent existence. They can be connected in a quantum way. Space does not distinguish between such entangled objects, and space cannot overcome their interconnection. It doesn't weaken their quantum interdependence. He says some people have interpreted this as saying everything is connected to everything else, or that quantum mechanics entangles us in one universal whole. After all, the reasoning says the Big Bang, everything was connected, so everything is still entangled now. However, he said, while I like such sentiment, such gushy talk is loose and overstated, the quantum connections between two photons emerging from a calcium atom in a process of entanglement are there certainly, but they are extremely delicate. In experiments, these have to be very protected and isolated. So the quantum entanglement becomes so spread out, if you were considering things were entangled at the very beginning together, is the Big Bang. And now they would be so spread out, he says, for all intents and purposes, the original entanglement would be erased. Okay, that's Brian Greene's take on it. Also, Niels Bohr has quoted several people in a book by Ken Wilber called Quantum Connections, and he pointed out that two of the pioneers of quantum physics, Bohr and Louis de Broglie, also made the point that in quantum mechanics, the distinction between the measuring apparatus and the object being measured have to be maintained. So even though these two men actually incidentally were into Eastern mysticism themselves and believed that at the mystical, in the mystical experience that things are seen as one, they didn't get that from the physics, they said. In the laboratory, in the physics study of nature, you need those distinctions. So that was very interesting to me. Also, some people take the connection to a more of a spiritual sense. And if there is any connection coming from the quantum physics, it's more of a physical connection. And also, we want to remember in the entanglement, they are correlations, not necessarily connections. So that's different too. And they're certainly not connections in the sense of communication being done at faster than the speed of light. One important point that I'd like to mention before I close is very often a person's predisposition, pre-existing worldview can affect their interpretation of quantum physics. Even Fritjof Capra himself, who wrote the Tao of Physics, said in a later book, he said, my presentation of modern physics has been influenced by my personal beliefs and allegiances. I have emphasized certain concepts and theories that are not yet accepted by the majority of physicists. So in that case, I think he's talking more about the bootstrap theory. But the first part does really apply, I think, to his applications and seeing parallels between quantum physics and Eastern mysticism. He had actually a mystical experience before he wrote the Tao of Physics, he says in the preface to the Tao of Physics. In a book called Quantum Questions, Mystical Writings of the World's Great Physicists, Ken Wilber, who is, and you may be familiar with him, he's very, a major proponent of what is called New Spirituality. He himself is a Buddhist, well, he follows Buddhist teachings, and he will consider himself a mystic. But he says he has this a collection of essays from the pioneers of quantum physics where they themselves said that we didn't get our mystical ideas from quantum physics. So you may wonder, well, why did some of these pioneers get into Eastern mysticism? Well, Wilber says it's because the physics did not give them what they were looking for. Because physics is looking at the material world, mysticism is looking at directly at the ultimate reality, separate things. Physics can't tell us anything about the ultimate reality, Wilber says. So I thought that was very interesting. Actually, in my research, I ran across just all kinds of backgrounds of people who are into quantum physics, quantum physicists, theoretical physicists. They come from Eastern mystic backgrounds, they can atheistic background, Christian background, and unknown to me background. So it really depends on your point of view, your predisposition, quite often how you interpret quantum physics. So, wow. So how does any of this matter to us? Does this apply to our lives at all? Do any of these implications, can you see how they might determine anything different in your life if you thought one was true or the other? These are questions that I've been asking myself. And for instance, the idea of free will. If things are probabilistic in the quantum world, they're not determined. Well, do we have free will like we think we do? You know, these are just things that philosophers, there's a whole area of study called the philosophy of physics, where these implications from quantum physics are being studied in great depth by great minds. And if you're interested, you could pursue some of that yourself. Well, is it time? Oh, we have 5 more minutes. Wow. Okay. Wow. I didn't anticipate that. So that's wonderful. Well, I just want to, okay, I'm just going to say, well, thank you, but I was just, as long as I do have a minute, let me step back and just say that I really, wow, recommend, where's my handout? At any rate, you have it there. And there are specific DVDs and, here we go. Okay, ones I would highlight. The World Science Festival. Brian Greene's on there. He's excellent. And in one of them, he's got Alan Alda doing the moderating. Well, what could be more fun than that? You know? So Alan Alda, it turns out, he has an interest in quantum physics and science. So that one is called The Invisible Reality, the wonderful weirdness of the quantum world. The other is Measure for Measure, Quantum Physics and Reality. The 2 World Science Festivals run by Brian Greene. PBS Space Time, fantastic. There's a guy on there who just loves quantum physics, and he's just fascinated by it. You can catch it by Contagious, you know. It's like, wow, I'm into this too suddenly. Veritasium, same thing. The guy's really excited about it. Looking Glass Universe. This is a woman. You don't normally hear about women theoretical physicists, but here she is. And everybody just loves her presentation. She's very humorous. So that would be one I would recommend. There are just on your handout as well, interesting topics to explore. The different things that we talked about today, I've listed them, so if you wanted to look into them further. I must say, quantum physics has just really challenged me. It's not my first language, as we say. I've really had to stretch myself to try to wrap my brain around it. But I wanted to. I really wanted to understand it. And I just encourage you. You know, they always say, good to use your brain. People go Sudoku puzzles or crosswords. I mean, hey, what's a better way to use your mind trying to understand reality? So I just recommend it to you. Okay.
So if you'd like to ask a question, please raise your hand. A mic will be brought to you, and then you can stand up and ask your question. Just remember the mic needs to be held really close to your mouth and preferably out. Yes.
Thank you very much, Pam. I thought that was excellent. I'm trying to make this practical for us as individuals and as a society at large. It seems to me the implications of quantum physics eventually have to make sense on a common sense level. And if quantum physics is anything, it's not common sense, but that doesn't mean it's not true. So as a society, we are still at the physics of Isaac Newton. How do we get the science of quantum physics? Is there anybody doing work that is taking these things and moving them into things that we can appreciate at the individual level and at a societal level collectively, so that some of this becomes common sense?
Well, that's a very good question. Like I said, I've done a lot of research on this, the internet, and people ask that question. In fact, one person said after the physicists were trying to figure out things, some person wrote in and said, can you guys just come up with a substance that will fill our potholes for more than a month. You know, let's make this practical. You know? So it's an excellent question, and I'd say Brian Greene is my first go-to person on that. He's trying to do that, and he's just doing a interface between the common man and the mathematician, the geniuses, and how to apply this to the real world. I would say he'd be the person, you know, and just read his book and look at his videos, and they will help you. If it can be done, he's doing it. And it's something to even ask him about, you know, write him a letter. He's got accessibility, so.
If I could address the last gentleman and just say that a lot of the high-tech revolution that you're having now was brought because of quantum physics.
That's right, yeah.
And you wouldn't have all the high-tech that you have now.
Yeah.
I just wanted to ask, I know you didn't have time to get into this, take days to do this, but something that's on my mind, I read 2 articles within a week about about dark energy. One said they used the lensing effect. They got a photo of what they think could be dark energy. The other article said that this other group used the lensing effect to help disprove dark energy. What are your feelings on dark energy? Do you think it exists?
Well, you know, to be honest, that's not my area of study, so I really don't know. But Brian Greene probably does. I would get the book and look it up here, and it's a great question.
Right here.
I don't know.
Hi, thanks so much for your talk. I'm wondering if you could comment about whether you think it's irresponsible of people like Rhonda Burns and people who write about philosophical subjects to take their own interpretation of quantum theory and sort of cherry pick the parts that work well with their spiritual philosophies, and then trying to say that, you know, there's this connection without really understanding or kind of caring about that there's any math basis to it.
That's an excellent point. And that is exactly what got me involved in this, because I was reading about these claims, and I thought, how can they say that? I don't remember reading that in quantum physics. So yes, it does bother me, and it bothers a lot of other people too. So I heard one person said, before you make claims about quantum physics, like for instance, well, I shouldn't name names, but Deepak Chopra uses quantum in his quantum healing book. And there's a great YouTube where Richard Dawkins is asking him, gee, why are you using the word quantum in your book? And he finally got around to saying, well, it's mostly like a metaphor. He's using it metaphorically. And so there's some aspects of it where your consciousness can affect your body, mind-body connection. And some people say, but see, even that is not proven by quantum physics. So yeah, it does bother a lot of people. And then it's good to challenge them. So over here.
This concerns your comments concerning Ken Wilber,
Yeah.
and you indicated that physics is not able to give folks what they are looking for, so some researchers turn to mysticism for answers.
Yeah. Mm-hmm.
Our understanding of quantum phenomenon just seems to be in its infancy. Looking ahead, is it possible physics will be able to provide the type of answers that people only get through mysticism today?
Well, that's a good question. You should read the preface to Ken Wilber's book. It's on your handout, the last one. And he spends like 40 pages talking about this very topic. But he says there's like different worlds. So one really cannot address the other. The study of the material world can't really speak to the ultimate reality, which is beyond the material. That's what he would say. Now, maybe someone else would say something different, but he would say that.
Okay, here.
I'm a newbie at this, and the reading that I have done and some of the experience is where music will affect the formation of ice crystals, where music will affect the health of plants. Mm-hmm. Is this part of what you're talking about?
Well, that's what they call, they're getting that into another level of it. There's a movie called What the Bleep Do We Know? And that goes into that. But that's criticized by other physicists and saying that's not been proven. You know, it's really more like a ESP, telepathy, paranormal behavior versus, you know, physics is more the studying the particles and the energy, matter. So it's different worlds. but some people make the connection though. Some people make the connection. Again, it's how much is consciousness involved in the results of these experiments. If you think it's very involved, and some people think it is, well then you go, well then it can affect the world around us as well. Now that may be a whole other field than physics though. It might be, you know, I don't want to guess, but telepathy, paranormal behavior, ESP or something. You know. Here?
Okay, here.
Hi, I wanted to address make a comment on the question that was made by the gentleman early on about the connection between what the physics says and how can we make this common sense. And I wanted to state that my science training came 50 years ago. And the teaching of science now, I think, will make the connection. Good science teaching is very different from what we all received. It's not mechanics anymore. It really integrates the whole field of energy. And it's kind of interesting how what you learn when you're young, you build on in your mind with your experience. And you grow with it. So I think there's a whole lot of potential for it to become common sense.
Great.
Okay, over here. Thank you for your talk. Some of it was enlightening, what I could understand. Seems like welding woo-woo and your basic mechanical physics, etc., is always going to be a dog and pony show. My question is, does CERN have anything to do with what's happening with quantum physics?
CERN, that's the particle, when they split the particles and, yeah, okay. Yes, it does, definitely. They are studying the subatomic particles and seeing their properties. That's talked about in Brian Greene's book, but definitely that's the lab work for quantum physics, is studying those subatomic interactions and what happens when you impact a subatomic particle at a high energy, high energy physics. Yes, definitely it's part of it.
Over here, I have another.
It's my understanding that a lot of these quantum physics, these gentlemen that are doing all this work, that the further they get into it, the more they start referring to God. What's your comments on that?
Well, that's a whole other topic, and I that'll be the next one. Yes, you're right, and even Einstein said God. Niels Bohr said God. The thing that we have to look into is what do they mean by God. Sometimes they're using a different definition for God than I would. Some people would say they're talking about nature. They're talking about the laws of nature. Even them themselves, like for instance Einstein, he may have started with, in fact I believe he did start with a personal, he was from a Jewish background, but he ended up in a more of an impersonal. He said he didn't believe in a personal God. So that can change over time as well. So, but a very fascinating question, and just to see the individual writers, when they use the word God, what do they mean? Some of them definitely mean the personal Judeo-Christian picture of God. Others don't. So yeah, but you're right. When you found that level, it's beyond us. It's beyond this world, and so they just naturally go into a supernatural level to try to explain, grapple with it. Yeah, it's natural. Yeah.
Okay, I think that's it. Do you have any more? Oh, one more. Okay.
Can you relate the idea of quantum physics with literature? You mentioned poetry, and I'm thinking specifically about Jorge Luis Borges and his fork of the gardening paths, which to me brought it down to a more human level and understanding.
Well, I'm going to look into that because I'm interested in poetry, so thank you for bringing that up. There is actually a whole online magazine called Quantum Poetry, so you can check that out. But what they mean by that, now I looked into these different uses of the word quantum. Sometimes it's used metaphorically. The pair of people who put out that poetry magazine said they're using that in the sense of they're looking for things that are not part of the norm, things that are out there, things that are not standard. So that's what they mean by it. But this, yes, definitely philosophy, these things all interrelate. So you can think in pictures about things. That's where the poetry comes from. And they try to do that with science, and that's where these analogies come from. So I'm going to look into that poem. Thank you. Last question?
Well, it's more of a comment, actually. For those of you who don't know, quantum mechanics is just a theory.
Yeah.
There has been no proof of it. There cannot be proof of it until they have a mathematical basis for it. And there's no mathematical basis. String theory is the closest they've got, but there's competing theories. So without that, it's a very successful thing. It shows great promise, but it could be all just woo.
Yeah, that's a very good point. Thank you for pointing it out.
I would like to end on that note.